This is going to be a demonstration of a program we wrote for computational tools for engineers here at BYU. The initial goal behind this project was to create a program that would ask a user for a string, to input a string, and then it would generate random strings until that string was reached. For each newly randomly generated string that the program's outputting, if it had an index that matched the corresponding index for the user inputted string, it would match, it would lock that index. That's kind of hard to visualize without a demonstration, so allow me to show you here. Let's say we want to guess this really long string. We can put maybe a letter in there, and you could have like quotes, hello. You can have whatever really you want in there, as long as it's within what we defined as possible characters. Possible characters are the lowercase and uppercase letters, and then it's also going to be the numbers, and then these other punctuative things. And so you'll see I run this here, and so what it does first is it generates, oops, sorry guys, it generates a random string that's of the length that you inputted, and then what it does is it looks to see what index it got right compared to your user inputted string. And so you can see when it gets a space, it's going to lock that, or when it gets a correct index match, it's going to lock that. And particularly the spaces are really easy to see. So you can see every time it's getting a space correct. It's also doing that for every character or number or symbol that it gets correct. So you can see as we get closer and closer to the bottom, it's getting more and more accurate until finally the string is reached. And then it returns how many iterations it took to get that string. And so this is not too particularly interesting. I guess if you wanted, like for example, at the beginning of movies, you know how they have like a demo, like a when they're displaying where the movie is being filmed at or whatever, like especially in military movies and stuff like that, they'll have this thing at the bottom of the screen that is like showing like where the location is, and it'll start something like this, and then it'll like generate through and then turn into wherever it is. So other than that use, this isn't too particularly interesting. So sorry guys, I have a head cold, and so I'm not talking or thinking very well. But so here on this function, what we did next is we said, let's do something where we can randomly generate a string of whatever length we want. So that's what this is. That's all it does. It just randomly generates a string from those possible characters I showed you before of whatever length you want. So then where this starts to get interesting is we say, okay, now let's do what we did above with the generations, the random generations, except for instead of printing out each random generation, let's just return how many iterations or how many generations it took to reach the target code. So you can see here, if I make a random string of length 1, that's what this guy is here. If I make a random string of length 1 and then see how many generations it takes to reach that, you can see if I run it once, it took 290 generations there. But obviously because there's randomness involved in this, this is going to be a different value every time I run it. For example, I run it again, got 14, right? So you can see there's quite a bit of variation in all this. And as a result of all that variation, you'll see later that we had to iterate this process like a ton of times and take the average. I'll explain that here in a sec. So what we wanted to do is say, okay, well, compare like a random string of length 1 versus like 100. You would think that if you had a random string of length 100, it's going to take a lot more generations now than just compared to 1. So there's 1 for 100, and surprisingly, it's only 300 generations. If we run it again, it's 400, run it again, 481. So obviously we're going to want to average here. But it's kind of impressive because as you increase in like complete orders of magnitude, your number of generations isn't increasing nearly as quickly there. See, I just generated a string of 1,556 generations. You can see at this point it takes the code a second to run. So I'm just going to make this a little bit smaller. So the idea here was to plot the length of the string, down here I'll show you, the length of the string versus the number of generations it took to get that string. And so you can see down here, as you get a longer and longer string, the returns on your length or number of generations that it took to get that string doesn't like exponentially increase. The reason why this looks so messy is because we did this like 50 different times, and so that way, because there's so much randomness in it, and so what we did is we averaged across each one of these, and that makes this much neater looking plot. So don't pay too much attention to this. Focus mostly on this. This is very interesting. This is a plot of the averages here of the length of the randomly generated string versus the number of generations it took to match that randomly generated string. And so why is this cool? Well, this is really cool because you can see as we have a string of length 20 compared to something around like 5 or so, you can see there's quite a bit of difference in the number of generations it takes to match it. But if we go between something like 60 and 80, you can see there's very little difference. Even though that was the same incremental difference between 0 and 20 and 40 and 60, there's very little difference as your string is bigger and bigger. And a real world interest of that is that when we're generating passwords, right, we want the password to be not hackable, and so basically if it's going to be hacked by brute force, where it's just randomly generating strings until it's matched, we want it to take the most number of generations to do that, or the most amount of time, if that makes sense. So it's kind of interesting to note that right around 40, a length of 40, maybe 35 characters, the returns after that of the number of generations it takes isn't very significantly different. It's not a lot higher, and so that was just kind of a really interesting observation we made. If you guys have any questions about any of this code, or if I didn't explain something and you're really confused, just shoot me a message on my YouTube account, and I'll be able to get back with you. Once again, thank you guys so much for watching this.